In the last video, we discussed the idea of stress, strain, and the modulus of elasticity. Here we're just taking the same idea, but now we're applying it to shear forces and shear loads. So the way that you can imagine it is, picture two plates that are like sandwiched together. Sandwiched together, and they're riveted. So imagine if I have like a little tube. So it's literally a tube, and then it's like there's like a head. Yeah. Say if it's like hammered in place, so then it just becomes. So when you see rivets anywhere, it literally just has this like a bob shape. And so that head is actually what you see. But anyway, so you can imagine just this center bit. I'm going to put that in red. Just this center bit. You can imagine that just like a little cylinder. And that's the part that's actually experiencing all the load. Yeah. Or the shear loads that we're talking about here. So I'm going to take like a cross-sectional view of this. Yeah. So here, I'm gonna say that the bottom is like fixed and the top is applying the force. The bottom can also apply the force, but let's focus on this part for now. So the way that we think about it is that just like how we had that stress is equal to the force on area, this applies for tensile loads. So just a separate situation where we have an object and we're pulling straight up on it. So it doesn't work the same way. Yeah. And it's the force divided by the cross-section area that we cut off here. Likewise, we are going to have a similar situation for shear stresses, where we get the shear stress, so that's shear stress, and that's going to be given by the shear force, divided by the cross-sectional area. But the way that we're taking the area is that it's like the area of the circle, so the top area. So that top area. So that's like the area that's being cut off here, that area. Yeah, so just to make this clear. So that's the shear stress experienced. Now, in regards to strain, you can imagine in this situation that if you apply a force like this, imagine it like a book, where it will kind of lean a little, and go across. Yeah. So now in our case, the change in length is what we're considering here, and that the original length is that height that we consider here. So the way that you can think of it is, now my strain, my shear strain, is my change in length divided by my original length. The other way that you can take this as well is treat this like a right angle triangle. I know this is very out of scale, but this would be my change in length. This would be my original length. And so you can take it as, this is my angle theta. And so I can say that this is also equal to tan theta. In this diagram, theta would be this little angle here. Theta. Yeah. And so now that we have stress, shear stress, and shear strain, we're also going to have, I forgot to write the original strain formula. So this is pretty analogous to just the delta L on L, just like that. But in our case, the change in length is pulling-wise the same direction. Yeah, you're going to also experience change in length there. So half of it's up, half of it's down. Yeah. So yeah, from like stress and strain, we're also going to have another, like a different version of the Young's modulus. See how we have the Young's modulus times the strain is equal to your stress, or I can rewrite this. This is the same thing as Young's modulus is the stress on the strain. Just rewriting the equation. Likewise, we're also going to have that the shear modulus is equal to the shear stress divided by the shear strain. And that's what we consider in the context of shear forces. Shear forces or loads. That's about it.